Okay, before we go on to something new, I just want to do one more problem with you with de Broglie's wavelength. And if we were in school, I would probably give you this half sheet. The first ones are all the photoelectric effect. So is the last one that I want to look at with you. But it's the photoelectric effect connected to de Broglie's wavelength. So it says, light strikes a photoemissive surface whose threshold wavelength is 580 nanometers. If the de Broglie wavelength of the electron is 1.561 nanometers, what color is the light that's striking the surface? Okay, so we have our lambda, whoops, right on the paper. Our lambda light striking the surface of the photon is 580 nanometers. And our de Broglie wavelength, which I'm going to do as a B for de Broglie, is 1.561 nanometers. Oh, wait, yeah, threshold wavelength, I lied. This is lambda O. And we're solving for lambda P. Okay? So I want to do this one because lots of times, sorry, that's just the last homework question. Lots of times people can get which wavelength is which mixed up. Okay? So it's giving us de Broglie's, which is the electron. It's giving us the wavelength of the threshold wavelength. So from the threshold wavelength, we can find FO because C equals F lambda. So F equals C over lambda O. So 2.9979 times 10 to the 8th meters per second over 580 times 10 to the negative 9. And when you do that math, you get an FO of 5.16879 times 10 to the 14th. Okay, so that's our FO. So of course we can get WO just equal to HFO. So it's equal to 6.626 to the negative 34 joule seconds times our 5.16879 times 10 to the 14th hertz. And so our WO becomes, equals 3.42484 to the negative 19. Okay? So that's our WO that we're going to use. So now we go to the de Broglie wavelength. And from the de Broglie wavelength, we can use lambda equals H over mv, and we can find V. So V equals H over m lambda. So it equals 6.626 to the negative 34 joule seconds. M, it's an electron, 9.109 to the negative 31, and 1.561 to the negative 9 meters, kilograms. V you get to be 4.6599 times 10 to the 5th meters per second. So once you have that, then you can do EK max, of course, is equal to 1/2 mv squared. So 1/2 9.109 times 10 to the negative 31 kilograms times 4.6599 times 10 to the 5th meters per second, and remember to square that. And so you get EK max to equal 9.89 times 10 to the 20th joules. So you have your EK max and you have your WO. So now you can go to EK max is equal to HF minus WO. And you can solve for your F. So F will equal, bring your WO over, EK max plus WO divided by H. So 9.89 times 10 to the 20th joules. And then our WO from up top is plus 3.42484 times 10 to the negative 19 joules. And then you're dividing by 6.626 to the negative 34 joule seconds. And when you do this, you should get an F of 6.6614 to the 14th hertz. But now the question asks for lambda of the photon. So lambda is equal to C over F. So 2.9979 times 10 to the 8th meters per second over 6.626 to the negative 34 joule seconds. And so you get a wavelength to be 4.50 to the negative 7 meters. And it wants to know what color is that. So then you go to this little chart and you look for 4.5. 4.4 to 4.2, 4.2 to 4.9. So it's blue. So you go back here and you say blue. Okay? So I just wanted to show you one of those, just to show you how they will all tie together. And you could be assured that I will give you at least one of those on your practice assignment so you can practice it. Okay? All right. So now it's time. We're still in the same unit, but we've finished now the calculations. So the homework tonight will not have to do with calculations. And now it's time to move towards models of the atom. So the first thing is, what the heck is an atom? Well, the word, and so it's a little history lesson here. So the word atom is Greek, and it was first used by a Greek philosopher, and if we were in class, I would make you guess which one. But the Greek philosopher is Democritus. I think this is the I, and this is the U. Okay, so he would have used it about 400 BC, and he used it because he suggested that every substance, everything you pick up, you look at, you see, could be broken down into smaller and smaller and smaller pieces until you finally got to the point where it couldn't be broken down anymore. And what you would have then, he said, was something that was called an atom. So he said an atom then was something that could no longer be further divided. And he was right. That's what the word atom means. The unfortunate part is that when we applied it, we didn't wait. We thought we got to the point where we thought we were at what was the smallest possible indivisible thing. It just wasn't. The word actually is defined as indivisible one. Okay? So now that was 400 BC. In about the 17th century, Robert Boyle brought the word back a little. And if you were in chemistry already, you might have heard of him, Boyle's Law. And Boyle's Law, he was studying gases. And he noticed that when you increased the pressure, the volume decreased, and when you decreased the pressure, volume increased. And so he suggested that the atom or the gas was made up of these little atoms that were separated by space, and when you increased the pressure, you pushed them together, and when you decreased it, you separated them. So he began to think of matter, of substances made up of these atoms. Then the end of the 17th century, and we're going to run out of time here, so it'll be continued. Two guys called Lavoisier and Proust We're measuring the amount of elements that